Hello, everybody in the lecture hall. Good morning, everybody on Zoom. Good morning, everybody from the future. My name is Gissin Fourny, and this semester we are going to explore together the evolutions of databases in the past 25 years or so, what we typically call big data. First, just checking, because it's the first week we use this room. Can anybody hear me on Zoom? Do you hear me fine? You can put a word in the chat. Sounds like a yes. All right, perfect. So you'll be able, of course, to ask questions in the lecture hall, of course, by raising your hands. We have microphones over there. It's going to be recorded, just so you're aware of it. If you don't want to be recorded, just ask to speak without a microphone and we'll repeat what you say. And on Zoom, you can also raise your hand, just like this, you see. It's after just a few seconds, just doing this or clicking on the hands at the bottom should do the trick. All right, and then we'll John Hao, who is right here moderating the lecture, is going to repeat your question. So today is going to be a bit special because I'm not going to actually teach you so much material of the lecture. I'm going to give you a history, an overview. It's more like an appetizer of what we are going to be doing. In the second hour, we are going to brush up on SQL. So if you visited information systems for engineers, that's just a repetition of what you know. If you didn't, then that's okay too. And it's an opportunity to learn SQL. It's really easy to learn. All right. So what are we going to do in this course, and what concretely are you going to be able to use for your projects here at ETH or in your PhD? It's to query data that might be a bit messy, not just a table like you would have in Excel, but something that might be messy with missing things, not clean everywhere. Can also be data of gigantic scales. It doesn't have to be both. Can be either gigantic scales or not clean data. And I teach you how to query it, use technologies in order to make use of it, typically clean it up, for example, to feed it into a machine learning pipeline, that kind of things, right? So that's just a quick summary. And we are going to be looking at technologies like Hadoop, Spark, JSONic, and RumbleDB that were developed here, among others, at ETH. Actually, 20 students or more actually built RumbleDB. All right, but in the end, this lecture is all about scale, big data. So just to give you an impression, our scale, that's the typical size of a human being, is the order of the meter, right? Between 1 and 2 meters. Now, if you zoom out, we live on a planet that the circumference of which is roughly 40,000 kilometers. And by the way, it's not a coincidence that it's a round number. It's actually how we defined the meter in the very early days before it was defined with the speed of light. We actually have a better unit to get rid of the 3 zeros. That's called megameters. Maybe you never heard megameters, but you heard megabytes. So that's probably not something that should surprise you. Then if we continue to zoom out, the Earth is in the solar system, roughly 150 million kilometers away from the sun. But now we can use prefixes like gigabytes, gigameters. So it's 150 gigameters from the sun, roughly. And if we go to this very big planet here, Jupiter, it's 1 terameter already, and the whole solar system, I'm being very generous here, is 1 petameter, right? If you go a bit beyond, you reach 10 petameters, and 10 petameters is a light year, what we call a light year. That's what the year takes 1 year to traverse. The Earth is actually part of something that we call a galaxy, because we realized we have not always known that, but galaxies look like this. We used to call them nebulae. And now we realize that we are in one of these, and the size is 1,000 hexameters. I'll come back to the prefixes. So you see, we keep having new prefixes for the distances. But that's not the end of it, because there's actually plenty of them. Oh, by the way, I can get rid of the 3 zeros with yet another prefix, the zeta meter. And if we continue to zoom out, there's actually billions and billions of these galaxies. The visible universe, what we can actually see, because light actually reached us, is roughly 138 iota meters. That's without considering the expansion of the universe, because if you consider the expansion of the universe, it's actually more than that. But basically, just that the age of the universe is 30.8 billion years, that gives us roughly that scale. So we are at the iota meter. What there is beyond that, we have absolutely no idea because we cannot see it. So maybe there's something else, maybe it's infinite, maybe it's finite and it just repeats. But the farther that we can see is iota meters. Now, it used to be that this is all the prefixes we had, but as we will see now, we have two new prefixes that were contributed that go even beyond this, but I'll show you the list shortly. But basically, the idea is that in order to explore such large scales, we are actually now at the Big Bang. We have to look in a very small with the particles, like the quarks, the electrons, and so on and so on. So the lesson here is for the very large, we have to look at the very small. So this is the standard model. It's what the universe is made of as far as we know. At least every time we try to break it, we don't manage to break it, but hopefully someday we'll manage and there will be new physics. Yeah, but so that's the infinitely small. And in fact, what I want to tell you with this is that the same goes for data. I like to compare data science with physics in a way, or with chemistry if you want, with the idea that with big data, we are reaching absolutely enormous scales. But in order to understand how data works at these scales, you have to think of it just like atoms and molecules. That data is also made of atoms and molecules. And we need to study these atoms and molecules of data in order to understand how we can query data at very large scales, right? The difference is that in one case, it's the real world. In the other case, it's kind of the data world. I would like to use throughout the semester something that's known as the Clicker app. It's actually developed at ETH. You probably know it from other lectures. So let me take this to calibrate. So you're supposed to go to this address right here in your browser, or you can download it from your favorite app store and then look for EduApp 3, right? I'm giving you a bit of time to do that. If you haven't already, just log in with your ETH credentials, right? By the way, times are changing because back then when I was a student, everybody had a laptop. So we all had our laptop in the lecture hall. And now when I observe the lecture hall, the proportions of laptop keeps diminishing. And now people have tablets or smartphones. So this is very interesting to see the evolution of this. All right. So let me switch right here to the view. And if everything works, you should be able to see the question. So the first time I'm going to wait for you to make it work. If you have any issue that we cannot resolve, there is a support, so you can write to support. By the way, it's not only for people in the lecture hall. Also on Zoom, you can actually use this app. So it's basically everybody can vote. Just not people on YouTube. That's the only thing. All right. By the way, I should scroll down because there's a lot of possibilities here. These are not the only ones. Have electrical engineers, we have a lot. Statistics, we have mathematicians here. Robotics, mechanical engineering, also we have a few of them. All right. 66. Is anybody having difficulties voting? No? All good? On Zoom, no difficulties? All right, so it seems to be working. Okay, so it's very good. So the lecture is intended for all departments of ETH. That's why it's called for engineers. There's also a big data lecture that's for master students. I assume that those of you who are computer science or data science is continuing education, so CAS, DAS, who are allowed to take any of the two. All right, I have another question for you. just to get an impression, have you taken the course Information Systems for Engineers last semester or the year before? So it's kind of half-half, right? So a bit less than half actually took it. Yeah, it's totally fine. I will tell you a bit about that, but it's totally fine. Okay. So now let me switch back to the slides. If I prepared everything correctly, we should get back exactly to where we were. I just need to let Zoom do its thing. Yes, exactly. Yeah. All right. Now here's what it looks like. That's the menu of the lectures. So there is Information Systems for Engineers, Big Data for Engineers. They are complementary to each other. Information Systems for Engineers is the 70s, 80s, 90s, and Big Data for Engineers is the 2000s, 2010s. You can take it in any order, really. It's totally fine. You know, like in the movie theater, you have the prequel of a movie and you can see it later, and that's absolutely fine, right? So if you took it, that's nice. You already know sequel. Otherwise, we'll learn a bit of it. But the material is sufficiently decorrelated, I would say, that you can take Big Data for Engineers even if you hadn't taken Information Systems for Engineers. All right. If you are a master student of data science or computer science, then you should take Big Data in the fall, not Big Data for Engineers in the spring. Continuing education, don't manage to say it. Continuing education, however, is totally fine. Okay. Now, if I continue, what I wanted to tell you between physics and data science, so one analogy is with the very large, the very small, and the atoms of data. Another analogy that I like to do is this 2x2 matrix. The idea is that it used to be, at least all the way to 1 or 2 centuries ago, that we were doing things with our brain or writing down, and we had mathematics and physics. So what's the difference? So mathematics is kind of ontological or necessary in the sense that you can just think and derive kind of everything, right? Philosophers might disagree, and I know some disagree, but basically you can derive a lot of things because it kind of has to be this way. Physics doesn't work that way in the sense that you have to experiment and see how things are actually working, right? So you design a theory and then you test it with an experimental protocol. And here it's because the world could have been different, right? The laws of physics could have been different. So we need to actually experiment in order to discover the laws of physics, right? However, of course, if you consider theoretical physics, it's amazing that you can still do a bit of physics from your armchair. Just if you have something beautifully simple, then there's kind of a hint that it might be the truth. But that's kind of an exception, right? Physics is about experimenting. Now, what is new is that now we have machines. So we can actually automate a lot of things. And all of these things with mathematics expanded into computer science. Now, what I mean with computer science is basically theoretical computer science, computation, computationability, algorithms, data structures, and so on. It's kind of also mathematical, right? In the sense that we can also do a lot of people wouldn't believe that, but a lot of computer scientists actually just use a whiteboard, just like the theoretical physicists. And then we have data science. So what is the difference is that in data science, it's kind of like computer science because we also use machines in order to query the data, but it's kind of like physics because we gather as much data as we can in order to learn about the world. So in the same way we did experiments with physics, we kind of query data in order to figure out how things are. The data could have been different, in which case the theory we would have discovered would be different, but that's basically the idea. So data science is at the sweet spot between computer science and physics, right? You can think, for example, of hypothesis testing for statisticians and so on. All right, so this is how we do science in these 2x2 matrix. You wouldn't believe if you read ancient texts, like thousands of years old, everything that our ancestors already figured out or kind of had the intuition, atoms and so on and so on. And Plato, for example, said the good decision is based on knowledge, not on numbers. That's why we need to query the data and extract actual information and knowledge from it. So since we are a few thousands ago, let's go through history. More or less, let me start with prehistory of databases. So how did we handle knowledge thousands of years ago? So roughly, humankind started settling 10, 12,000 years ago when the temperatures rose a little bit. Back then, all we had was our brains and speaking. So people would just tell each other the knowledge, transmitted from generation to generation. Some people would sing, actually. So that was, of course, a lot for the famous people like the kings, the queens, and so on, the emperors. But basically, all of that knowledge was preserved and transmitted from generation to generation. The problem is that you can lose information or you can distort information. Thus, there was a great invention that followed, which is the writing. My clicker is actually, yeah. So writing was the way that we could encode information or knowledge that could be preserved for thousands of years. And in fact, we can see it because we discover all of these tablets today that we keep deciphering, and now with artificial intelligence, we keep deciphering even new ones that we couldn't before. So that allows us to avoid the distortion and the errors when we transmit the knowledge, because we see that exactly as it was thousands of years ago. So that's the writing. So this is one kind of tablets that we get with actually just text, right? It's telling a story. But there is another kind of tablet. There's two big families of tablets that looks like this. It's not text. And in fact, when I looked at that, it felt like I was looking at a science fiction movie where people traveled back into the past and brought some ancient technology, because that almost looks like an iPad, right? Running spreadsheet software. And in fact, that's the oldest relational table that I'm aware of. And that's 4,000 years, 3,800 years. So this is incredible. And that's a relational table. It has columns, it has rows, it has everything. So what we learned from this is that tables are very, very, very intuitive to human beings to understand. Even our ancestors actually knew that. All right, so it's called Plimpton 322. This one contains some Pythagoras triples, the sides of a rectangular triangle, a right triangle. All right, then we found a way to easily duplicate information, because before we had printing, people needed, typically monks, needed to manually copy books after books. When we invented the printing press, Gutenberg, for example, we were allowed to suddenly print thousands or millions of copies of the same text. So that accelerated the propagation of knowledge. Then there was the golden age of the press, for example, in the 19th century, where information propagates very fast. Then we automated and made things even faster with computers. So that's quite old. It's the time where computers would take an entire room that would consume more electricity than the rest of the city. In fact, if you switch it on, then the power of the city goes down, which is unfortunate. And that had less power than the smartphones you had in your hands, and by orders of magnitude, just to see the evolution. But that allowed us to automate and make things faster, first mechanically, and then with silicon and transistors, even more so, right? Now, we are still in the prehistory of databases, and that's the 1960s, where we have file systems with directories and files. You probably are all familiar with that, even though on smartphones we don't really see them, but on a laptop you do have still exposed the directories and files. And in the 60s, this is how people were dealing with data. They were storing the data as files, and they were trying to make do with it. But it wasn't very practical. And in fact, it was so impractical that there was a turning point in history by somebody called Edgar Code, who realized that we have to shield the users from the complexity by just giving them some simple model like a table, thousands of years old, with rows and columns that they can process, right? So that was the fabulous idea by Edgar Code, and that's called data independence. I'm going to keep repeating this one the whole semester, because it's not just for information systems for engineers. It's also for big data for engineers. And then now we are going to focus a bit more on this. In the 2000s, we had new technologies, the key value stores, the column stores, triple stores, document stores that kind of give new ways of handling data. So we'll take the time to go through this during the semester, maybe not triple stores, but the other three a little bit. Now, big data, let's come back to big data after this historical perspective. So first is the buzzwords. Buzzwords come and go. For example, what are the buzzwords? So at the moment, I think the buzzword is AI, artificial intelligence. There's even artificial intelligence and machine learning kind of go together. It used to be that the buzzwords was the blockchain and Bitcoin, so everybody was doing blockchain. Before that, it was cloud computing and so on. And even before that, there was at some point biotech. All the company names would end with Otron, even the burger restaurants. So when you see companies that sell iced tea renaming themselves as the blockchain, that's actually not a new thing. But anyway, it's all buzzwords. And when there is a buzzword, it's important to just stay away from the distraction, right? So now big data as a buzzword is kind of fading away, even though it's still a little bit there because it's shifting to AI. But we need to define what we actually mean, because whenever there's a buzzword, it's hard to define what it is. So I'm going to try to do this today. Then there's going to be a lot of companies there, because a lot of what happened in the past 25 years was driven by companies, because these were the ones that had the data that they couldn't deal with anymore with older technologies. So they invented all of this. So you're going to see a lot of companies. It's not because they pay me or anything. It's just that this is just what happens, right? Now, big data is often associated with something we call the 3 V's of big data: volume, variety, velocity. There's a fourth one that sometimes we add, which is veracity, but I'm going to focus on these 3. I'm going to go one by one through this. You will see that looking at big data through this picture is a pretty good pair of glasses to look at things through the entire semester. So if I start with volume, the volume of data, first, we have so much data because we can. We can store it. We have all of the hardware that we need in order to do that. So it kind of happened that companies are hoarding data because they can. I'm not going into data protection, which is a very important topic as well. And it's not because you can doesn't mean that you're allowed to do that. That's you need to act responsibly. But basically, we can store data. Then data carries a lot of value, and we can see all we extract from data can lead to decisions that can be made in an optimal way or for scientific discoveries. And the more data you have, it's exponential. So if you take 2 pieces of data together, the sum of these has even more value. Why? Because you can join. I'll come back on the joins, of course, for those who don't know that. So it's actually growing exponentially in terms of utility. And that is also why, when you look at data protection, the concentration of data into the hands of the same entities is something that one needs to be careful about, precisely because of this, right? There is a course called, I think at ETH, Big Data Law and Policy. That is a guest course that might be interesting for those of you who are interested in these aspects, like ethical aspect and legal aspect of data. And then we have a lot of products that require all the data. If you want to compare flights or hotels or restaurants or trains and so on, then you need all the data. So that's one more reason. Now, because we accumulated so much data, we needed prefixes to deal with them. And these are here. You must know them by heart. You probably know the first ones. If you don't know tera, peta, hexa, zeta, and so on, think of the Greek for 4, 5, 6. So tetra, penta, hexa, tera, peta, hexa. It's the number of groups of 3 zeros in Greek, right? So that should help you a bit. Actually, it's on purpose that it resembles a little bit like Rona is like nonna and so on. All right, so this is something you have to know by heart. Rona and Quetta are actually new. They were not here when I started teaching big data, but they were added. I think the motivation was the masses of Jupyter that also needed that many zeros, but there are also some users that started running out of zeros, running out of prefixes. So here it is. We don't have yet I think maybe ronabytes or quetabytes, we don't hear so much, but it's probably going to happen at some point. Supposed to switch the slides. If I press again, it's going to switch too much. No, okay. Okay, now I have a question that I need to ask you. And here it is. From what quantity of data do you consider it to be big? Would you say it's gigabytes, terabytes, that you might know because that still fits in your laptop, petabytes, 1,000 terabytes, or an exabyte, 1,000,000 terabytes? What do you think you would call big data? We have a majority, and in fact, this majority reflects the majority, I think, of what people would commonly call big data. Typically, we think of petabytes. Why? Because it doesn't fit on a machine, and typically that's what you have in a data center, the size of data, but we'll come back on that. Terabytes could be considered the beginning of big data. It still fits on your laptop, right? You don't need a data center for that. But we will see that there's many cases, in fact, maybe 80 or 90% of the projects that do fit on your laptop. And then you should do it on a single machine, much less expensive, and you can optimize much more. But I'll come back to that. So what we are going to learn will also be usable on your single laptop without needing an expensive cluster. An exabyte, here we are at the scale of the whole of humankind, right? But this is accelerating so much that now we are probably stepping into the zettabytes. You really need to consider that the quantity of data we create in just a few years, 2-3 years, is the same order of magnitude as everything that's been created in millions of years, right? In just 2 or 3 years. This is telling you how the acceleration is in terms of the data that we are producing, right? So exabytes, zettabytes, I think we probably are way into the zettabytes now, probably. And the total quantity might even be in yottabytes by now. So let me switch back. Again, if I prepared correctly, we are supposed to land back exactly where we were. Yep. All right. So these are the prefixes. And as you can see, in terms of data, since we started accelerating from the first computers, we went all the way to not only to Jupiter, but almost to the Milky Way, right? So this is what we did in just a couple of decades, right? So this is impressive by comparison, right? And by the way, you should know the prefixes. There is another series of prefixes, which is for people who love powers of 2. You might have heard that for some computer scientists, when they tell you a kilobyte, it's actually 1,024 bytes and not 1,000. And somehow there was this ambiguity. It was resolved eventually with different prefixes that are meant to cover the powers of 2. As you can see, 2 to the power of a multiple of 10 is very close to a power of 10, but not exactly a power of 10. So 2 to the power of 10 is almost 10 to the power of 3. It's not that much used, but you should know that these exist. Of course, you don't need to know these numbers by heart, even though I suspect that some computer scientists might know some of those by heart. But just know that they exist, basically, without learning anything by heart. All right, so that's the volume. Now, the variety. The variety is simple. Tables is what we used to use in the 70s, but there are also other shapes of data, trees. We are going to focus on them during the semester a lot. Data can be shaped like a tree. It can be shaped like a graph in graph databases like Neo4j. It can be shaped like cubes that actually we cover in information systems for engineers. It's the slice and dice of the business reports that a company can find, for example, balance sheets and so on. And then there is text, which nowadays actually is probably growing even more popular than the rest of the databases with ChatGPT and LLMs. This is covered also in a lecture, information retrieval, that I give to computer scientists, but this is a fifth way that the data can actually be shaped. All right, so 5 of them: tables, trees, graphs, cubes, and unstructured data, text. The third V is data velocity. So we keep producing the data. As I told you, by now we are way into the yottabytes range of what we produced. But I'd like to show you the challenge that this represents, because you might think, okay, we just produce more data, but we also have the technology to read it and process it, right? So why is that even a challenge? We just can handle it, but no, it's actually not that simple. And in order to understand that, I need to use 3 terms. Not everybody might have the same definition, but I'm going to use them in this way for that purpose. The capacity is how much data can you store. For example, a hard drive has a terabyte of data. That's the capacity of the hard drive. That's the first thing I want to look at. The second thing is the throughput. It's the speed at which you can read, right? How many bytes per second can you read off the hard drive? You can also experience that as the download speed from the internet, right? When we see it's a gigabit connection, die schnellste Schweiz der Welt, that's typically throughput, right? And then latency is the third one. It's how much do you need to wait until you start receiving data, right? Because it's not instant. You probably notice when you're on the internet, you might have a delay of a few milliseconds or a second before the page actually appears, right? So that's called latency. Some people use the term latency to measure all the way until you have received everything, but here I just mean from the moment you start receiving something, right? Now, how did these 3 evolve? This is where we can learn something. I tried to find the oldest commercially available hard drive, and I found this one, 1956. IBM Ramac 350 was part of a computer that IBM was selling. It had a capacity of an incredible 5 megabytes. It had a throughput of 12.5 thousand characters per second, bytes character, you can consider the same thing. And the latency was 600 milliseconds. The dimensions were like this, was like 1 meter, 1 meter 70. So absolutely gigantic, right? To store all of that. The reason for the latency 600 milliseconds is that inside that, there are these rotating disks that you need to read. And you have a reading head that reads the bytes from it. But in order to access a specific byte, you need to rotate all the way. So you need to wait until the disk has rotated to bring the byte you want to read under the reading head. So this is the reason why there is that latency, and you need to wait until you start reading. Okay? And how did that evolve? Well, this is what we have today. That's the largest HDD, the hard drive. I didn't consider SSDs. You could also, but this is the largest HDD that I found today. And I need to zoom in because actually it's so small. It has 26 terabytes of data, typically used in data centers. I don't think many people have that for their laptop, but it has the merit of existing. The throughput is 261 megabytes per second. The latency, roughly, I took it from another model, but that's the right order of magnitude, 2.3 milliseconds. It's less because it still rotates, but it's much smaller. And the dimension is like this, right? This is the sort of thing you have in your, not in your smartphone, but in your laptop, right? Now, how does it compare? So I ran a comparison. Thinking, do I ask you this question? Maybe I keep it for later, this one. So I ran a comparison. The capacity are renormalized per unit of volume, right? Because otherwise it's not fair. There's one that is huge and the other one small. So I renormalized by the unit of volume, and I found the progress to be this. And this is already here on the slides. This is there. You have an increase of the capacity by 20 billion times the factor. Throughput, the speed at which we can read, is only 20,000. That's ridiculously low compared to the increase in capacity. And latency improved. Here is the opposite. It decreased by 250. That's ridiculous, right? So even on a logarithmic scale, you can still see the difference. And in fact, this is why we are in big trouble. And just to illustrate why we are in big trouble, just with an example, imagine that instead of hard drive, I use books. So let's take a book today that has 600,000 words. That would be the capacity instead of bytes. The throughput, that's how many words per minute I can read. Let's say 1,000 words per minute is what people can read. I round it, right? And then the latency, but here I care less about this one, is you go to the shelf to get the book, so that's 1 minute, right? To get the book and start reading it. Now, how much time do you need to read a book? Well, 10 hours sounds reasonable, right? Maybe less if you took the latest novel by Dan Brown or something, and maybe you read it even faster because you're excited, but 10 hours is kind of reasonable. Now, if I go to the future, let's say 2 centuries from now, and we evolved with exactly the same factors as for the hard drives. I'm taking factors that actually happened, right? 20 billion times capacity, 20K for the throughput, and so it actually happened. I'm even giving 2 centuries for that. Then this would be the capacity of a book in 2 centuries, and the number of words per minute we can read would be 21 million with the same evolution factor. Well, to finish the book, now we need 1,100 years compared to 10 hours. We are in big trouble because now we produce so much, we cannot even read it fast enough, right? So this is why we need to come up with new ideas. And this is why we parallelize and we batch process. Parallelizing means that instead of a single person reading the book, you spread it all over 200 million people. Each of them reads a small part of the book. And that's it. Then you can do it in 10 hours. That's the secret of querying data that we'll see in this course. Right, so this is why we are going to use so many machines. It's to fix that challenge and the distortion in the evolution of capacity and throughputs. Right. The other one is batch processing. I'm not going to tell so much about it today, but we also are going to look at how to solve for the discrepancy between these two. It's a bit more complicated. So that's what is big data according to me. It's that we have a huge challenge because capacity, throughput, and latency did not evolve at the same pace, and that forced us to come up with new technologies in order to deal with it. It has a huge impact in the sciences. I'm going to give you just a few examples. One of them is CERN, high energy physics, where they produce 50 petabytes per year. Maybe it's even more now. They have 10,000 servers, hundreds of thousands of cores, and you can follow the latest evolution. There's an address here. In fact, they produce so much data when they collide the particles that a lot of it is just thrown away. They don't even bother to store it. And they are trying to come up with machine learning-based ways to select what you throw away and what you keep. But this on the left is what you keep. It's not even the whole data generated by the collisions. All right, and there's a link to databases. There's this paper that we wrote in my group about the usage of why are they not using SQL? And because it's a database problem, really, to detect the Higgs boson. So yeah, that's for anybody interested. And after this course, you should be able to understand that paper. Next, we have cataloging the sky, right? All the galaxies, the planets, and so on. So here too, we are trying to gather data. That's the Sloan Digital Sky Survey. That's yet another example. Yet another example is the DNA. Right now we have also CRISPR, RNA vaccine, and so on and so on. That's bringing the data also to these very interesting molecules. And in fact, some people, including some that were here at ETH, managed to execute SQL on top of DNA. Literally, like this is hardware, this is the DNA, and they execute relational queries on top of that. So this is all very exciting. What's going on? All right. Oh, there's the sun. Let me see if I can maybe remove this curtain. We have here the sun that is basically hitting the slides in the lecture hall. So I need to find a way. Where is it coming from? Probably from the back. Let's see if that does anything. Okay, let me do the other two. That's strange. It's not changing it. Oh, yes, yes, now it is. Okay. So now the light is disappearing. Okay. So the scope of the lecture is databases. So there's this way of looking at data, information, knowledge, wisdom as some sort of pyramid. And we are interested in databases, right? Querying the actual data, not machine learning, not artificial intelligence. It's very exciting and there are connections, but this is not the focus of the lecture. I'm going to reopen the curtains in a more optimized way after the break, don't worry. All right, so now this is the lecture team, right? So they are right there, some of them. So we have Ludovica, who is here. We have John Rao. You can stand up if you want. We have John Rao, we have DK, we have Zombor, and we have Alexandre. Any other TAs? Yes, right here, Ragnar. All right. We also have a new TA that we hire. Well, I'm not calling her a TA. It's Ethel that you can see right here. The reason I'm not calling her a TA is an AI model that you can ask questions. You can connect to ethel.ethz.ch. There's a link in the Moodle. We train her with the entire textbook of the lecture, all running on ETH premises, and you can chat with her all you want. I recommend that you consider her a fellow student, right? She can make mistakes. You know that ChatGPT also hallucinates, but she's also part of the team. All right, so let's applaud the TA team to encourage them. And so you will have exercise sessions with them, not this week, next week they will start. So no exercise sessions this week. This week, the goal is just to install the Docker Compose. You will be instructed, check that it works. And if it doesn't work, then there is support that is going to be organized, okay? Now the overview of the lecture looks like this. We are going to look at how to store data, the models of data, the processing of data, even including in data centers, and the management of data with query languages on the higher level, right? So a lot of interesting topics in there. What is expected is that you attend the weekly lectures in the lecture hall or on Zoom. That's fine too. You can also watch the recording. Some people even binge watch the recordings at the end of the semester. Just a word of warning, if you binge watch the recording at the end, you might pass the exam, but then you're going to forget everything. The best way to remember what we are going to be learning through the rest of your life and your career is to really try to learn every week during the semester. This is how you remember in the long term. Okay, so then there's the exercise sessions. There's going to be some material to read, even though now a lot of it is going to be the textbook to make it easier. And then there's a written exam in the summer session, 180 minutes for you. I'll tell you more about that later. We have 25 bonus points that you can get, a few of them every week. You have quizzes to solve. Every quiz that you pass gives you 0.01 points, and they are added to your exam grade at the end. And you basically, before the grade is rounded to a quarter grade, right? So this is an opportunity to improve your grades at the exam, right? So we encourage you to solve the quizzes during the semester. If you have a disagreement on a quiz, write an email. It's totally fine. Try to have a discussion. Maybe you give arguments, and maybe we accept no answers. So it's totally fine. In fact, it's the goal of that, to bring you at a level that you can have a discussion. Then we have the textbook. Here, there's a printed copy available, but it's not up to date. If you really want the latest, just download the PDF. I will once in a while upload a new version. If you see errors, let us know. So this is the address here. You can just download the PDF online just like that, right? Stored on the ResearchGate website. Okay. And again, I insist, it's free. Online. You don't have to buy it. You don't have to pay for it. The library, if you want a printed copy, the ETH library has, I think, a few copies of it. But the latest version is really the one you get on that website for free. Then we will have Docker. Every week, we'll use a setup for the programming assignments, and it should just work. There's the Docker Compose commands that you run. Try it this week, and if you have any issues, then the TAs are going to help you. Next, there is a chat. using elements, go to chats.ethg.ch already now, actually, using your login credentials. We will then invite you in a batch, like batch processing. We'll invite you all to the chat room of the course. There is also the Moodle with a forum Q&A. So this is where you have guaranteed answers. If you ask questions on the Moodle forum, this is where the material of the course is also going to be stored, all the slides, recordings. The link to ETH is also there. And ETH, of course, this is a screenshot of what it looks like. It's designed right here at ETH. Gerd Kortemeyer is in charge of it. One of our former TAs, Susie, is also involved. They have students writing their master's thesis with them on this. It's really amazing. We tested it. It's not perfect. It does mistakes, but it's really, really amazing. If you click on the little book image, it points you to the parts of the textbook that it used to produce the answer, right? So again, use with care, but hopefully it should support you a little bit in your learning, right? Which brings us to the break. So we are going to have a break of 15 minutes. So I see it's 1 minute past 9. So I'm going to see you at 16 past 9 for the continuation. And in the second hour, we'll brush up on SQL and relational databases. See you in 15 minutes. Thank you.